Okay, what does the universe expand into? Well, now if you would argue that like basically dark matter is the same stuff as what started the Big Bang, so then you would have basically white holes bursting forth. However, to the naked eye, while that was happening, you would have, I guess it would be a time dilation, where time within that was sped up too fast. So it would be incredibly hard or impossible to try to go into a space like that. However, our entire universe, could also be in a time dilation. So right outside our universe is just more universe. However, we're going at a faster rate. And when we hit equilibrium and reach the same time, basically, as what's behind us, then it'll open up. And the way in which viewing it is to view time more like a fluid than like it's like the fluid we're living in. You can argue that it's a dimension, but I don't think that's the right way to view it. I would say that our version of time is a single dimension that we're living in, and there's other ways time is acting out. In the quantum world, I would argue that time is going at such a fast rate perpetually. So it's a different layer.
We expand with the universe? And could it be that the universe doesn't expand, but we shrink? At the end of this video, you will know the answers. I haven't made a video about this so far because there are already lots of videos about it. But then I was thinking, if you keep asking, those other videos probably didn't answer the question. And why is that? I'm guessing it may be because one can't really understand the answer without knowing at least a little bit about how Einstein's theory of general relativity works. Hi Albert, today's all about you. So here's that little bit you need to know about general relativity. First of all, Einstein used from special relativity that time is a dimension. So we really live in a four-dimensional space-time with one dimension of time and three dimensions of space.
And I think that's kind of the wrong way to view it. If I go into water, there is this other thing that you could kind of view as like a different dimension. Okay? It's acting out. However, it's a viscosity type of a thing. It's a fluid. So if you view all of time and space similar to that, then you're acting out with it as you would a normal fluid.
Without general relativity, space-time is flat, like a sheet of paper. With general relativity, it can curve. But what is curvature? That's the key to understanding space-time. To see what it means for space-time to curve, let us start with the simplest example, a two-dimensional sphere. No time, just space. That image of a sphere is familiar to you, but really what you see isn't just a sphere. You see a sphere in a three-dimensional space. That three-dimensional space is called the embedding space. The embedding space itself is flat. It doesn't have curvature. If you embed the sphere, you immediately see that it's curved. But that's not how it works in general relativity. In general relativity, we are asking how we can find out what the curvature of space-time is while living inside it. There's no outside. There's no embedding space. So for the sphere, that'd mean we'd have to ask how we can find out it's curved if we were living on the surface. Maybe
Okay, so the reason why this is... if you have basically bubbles instead of... So you have different bubbles. You have this fluid, it bubbles up. So every little bubble is coming up. We have the initial bubble that we're in. However, there's more bubbles trying to form into it. And these bubbles can distort this sphere so that where there's dark matter coming into existence, you have this new bubble forming, having this one grow, but it'll push out in weird ways until it like pops. And then at some point, sure, it might try to reform a spherical thing, but you've got too much of this coming all over the place. So you have constant little bubbles all over here. So there's no way to figure out exactly what the shape of our space-time dimension actually is, because it's growing at a thing that's not, it looks irregular. Just just blow a bunch of bubbles. See how one big bubble can form all these crazy little shapes. And then you grasp how our universe is expanding right now. One bubble might grow a little bit faster or have more force. So then you get like a distortion in one area, and then that's that little bubble. That's that little dark matter just forming a distortion here.
Ants crawling around on it. One way to do it is to remember that in flat space the inner angles of triangles always sum up to 180 degrees. In a curved space, that's no longer the case. An extreme example is to take a triangle that has a right angle at one of the poles of the sphere, goes down to the equator, and closes along the equator. This triangle has three right.
And if dark matter is having this expand and with little bubbles, and maybe, just maybe, our bubble is actually one of the smaller bubbles in a larger bubble in which space is acting out at this time. So if you view space-time like density, if you have something more dense, then it's almost like a wall around it. And so basically, to have it like interact, they need to be at these, there needs to be an equilibrium. So time has to catch up. So what's ever outside of our time space, if we've not caught up to the exact time it's in, then it's distorted. Then we are a little to an observer. If there was an alien species trying to look into basically dark matter in its universe, it'd be trying to go into our universe. So if you want to have like a crazy theory about aliens and why they keep popping in and out of our universe, well, maybe they're just trying to come in. They can only stay here for a little bit because our time's going too fast for them. So if they stay for too long of a period, it could be years on the other side. If they stayed a day, who knows? Who knows where we are at this time dilation? Earlier on, we were faster because that's how it would work. Until we reach equilibrium, we will be going at a faster rate than what's going out. And eventually, we will catch up if there is a larger universe that we're actually in. We will eventually catch up, and basically, what we view as this reg will just dissolve, and you'll just see more universe. So, who knows? You're dealing with bubbles. Just perpetual little bubbles just growing out of each other.
Right angles. They sum to 270 degrees. That just isn't possible in flat space. So if the ant measures all these triangles, it can figure out that it's crawling on a sphere. There is another way the ant can figure out it's in a curved space. In flat space, the circumference of a circle is related to the radius by 2 pi r, where r is the radius of the circle. But that relation too doesn't hold in a curved space. If our ant crawls a distance r from the pole of the sphere and then goes around in a circle, the radius of the circle will be less than 2 pi r. This means measuring the circumference is another way to find out the surface is curved without knowing anything about the embedding space. By the way, if you try these two methods for a cylinder instead of a sphere, you'll get the same result as in flat space. And that's entirely correct. A cylinder has no intrinsic curvature. It's periodic in one direction, but it's internally flat. General relativity now uses a higher dimensional general.
The problem here is the quantum world looks as if it's a projection, right? So you have this world that we view as the quantum world. But what would happen if the quantum world, aka its space, was completely a different dimension? Completely a different, an utterly different consistency than even what we're expanding into. The quantum world is just existing at a density. And the difference between that is like oil on water. Okay? Our universe is acting out as the oil on the water. And so it looks like it's flat because we're not noticing that the quantum universe is this separate dimension from us. And everything that gets close enough to it is interacting in a way that looks like a projection onto us because we're not seeing. Everything's in a separate dimension down there. So it looks like we're acting out on a two-dimensional pad. So everything looks like we're being projected out. Thus the theory, we're in a video game. However, okay, who knows? I'm not going to disagree. I don't know. If we're in a video game, how would you, like, if we were literally like a computer simulation, don't know how to argue that. However, you're arguing that purely because you look at the quantum world and everything looks as if it's a projection. Now think about that. If I have a rock in water and I skip it across, and imagine where I'm skipping it, because water's thicker than us, I can skip a rock faster, and I can skip it so much faster that if you're a fish looking above, it would look like it was in 3 different places at once. And where it hits, you could literally take pictures, and it would look like that rock was actually in the water, even though it skipped along. You could see it, everything you would do. However, the closer and closer you looked at that rock, you'd realize it was a projection. If you were that fish studying people skipping rocks across the surface, if your whole life was to look at that, it would look as if everything was a projection. Because you don't understand, stuff is acting out above our space-time.
Illusion of this intrinsic curvature. So the curvature of space-time is defined entirely in terms which are internal to the space-time. You don't need to know anything about the embedding space. The space-time curvature shows up in Einstein's field equations in these quantities called r. Roughly speaking, to calculate those, you take all the angles of all possible triangles in all orientations at all points. From that, you can construct an object called the curvature tensor that tells you exactly how space-time curves, where, how strong, and into which direction.
Unless your assumptions are to put things in as if it's acting out with our density. As in, time's pretty much going like how we are right now. However, if like dark matter is at a completely different density, time is traveling incredibly fast in those little pockets until it reaches equilibrium, you're not going to be able to use this equation. Because it's only functioning in a way. You're not getting all the things. If you understand how it's acting out, what the time is, what the scale is within those bubbles, like how much energy, how much matter, and you figure out that, then you could start calculating the shape of the universe. But you would have to understand what's going on in each patch of dark matter and dark energy. The dark matter versus how much dark energy would probably, if you could really calculate every little bit, would probably tell you exactly how this thing is developing. And then you could try to use like the background radiation map, and then you'd understand basically, okay, this was the initial bubble, and then you see like the darker patches, those were more patches, and then you'd start calculating out all this dark matter using the dark energy, and then you'd start figuring out a weird little shape to create, and then you could create a model. But you'd have to get so much more information than what we have.
The
and honestly, it doesn't look like a circle.
Are sums over that curvature tensor. That's the one important thing you need to know about general relativity. The curvature of space-time can be defined and measured entirely inside of space-time. The other important
But everything acting out in space-time is different because we have these other little pockets of dark matter and dark energy affecting us. That's the reason why the universe is expanding exponentially. Because there's so much more force. There's more matter coming in. When these little pockets of dark matter happen, and you probably see it as like a weird, when it hits, you probably see like the initial light escape, like a giant explosion. And then when that wave goes across, then you start realizing, oh, this pocket that we thought was dark, you see light, and then it's now in our space-time type of a thing.
thing is the word relativity in general relativity.
Yes.
That means you are free to choose a coordinate system, and the choice of a coordinate system doesn't make any difference for the prediction of measurable quantities. It's one of these things that sounds rather obvious in hindsight. Certainly, if you make a prediction for a measurement and that prediction depends on an arbitrary choice you made in the calculation, like choosing a coordinate system, then that's no good. However, it took Albert Einstein to convert that obvious insight into a scientific theory, first special relativity and then general relativity. So, with that background knowledge, let us then look at the first question. What does the universe expand into? It doesn't expand into anything, it just expands.
Nah, maybe. Maybe. Or we are a patch of dark matter to a larger universe. And so when our time space hits equilibrium, the densities are no longer different. And it dissipates out. Then we will see the larger universe that we now exist into. Which will be so much bigger than we could ever comprehend. And likely, my money's on that.
The statement that the universe expands is as any other statement that we make in general relativity about the internal properties of space-time. It says, loosely speaking, that the space between galaxies stretches. Think back of the sphere and imagine its radius increases. As we discussed, you can figure that out by making measurements on the surface of the sphere.
Yes, if you have bubbles and you're blowing bubbles, the bubble keeps getting bigger. However, sometimes little other bubbles start forming into it and start distorting out this bubble. And you get all these other little bubbles distorting. And sometimes all the bubbles can come into one giant bubble at the end, which would be like all the dark matter coming to equilibrium with this. And then you'd have like this giant sphere. However, more than likely, there's another larger universe. And so when this thing quote unquote pops, then everything that was in this bubble is now in a bigger thing.
Sphere.
A wider universe.
You don't need to say anything about the embedding space surrounding the sphere. Now you may ask, but can we embed our four-dimensional space-time in a higher dimensional flat space? The answer is yes, you can do that. It takes in general 10 dimensions, but you could indeed say the universe is expanding into that higher dimensional embedding space. However, the embedding space is by construction entirely unobservable, which is why we have no rationale to say it's real. The scientifically sound statement is therefore that the universe doesn't expand into anything.
Okay. However, if you can start looking at it as a time dilation, so the wider universe that we're pushing into would possibly be at a different time. And understanding that, then you'd start figuring out how it's interacting with us.
Do we expand with the universe? No, we don't. Indeed, it's not only that we don't expand, but galaxies don't expand either. It's because they are held together by their own gravitational pull. They are gravitationally bound.
Okay, so the Big Bang happened. the Big Bang displaced possibly a larger universe, basically, okay? So, if you think about like something bubbling up to the surface, if you had a fluid that had multiple densities bubbling up, and so you have this first bubble that's of this density, and then the newer bubbles are at different densities. You could imagine, like, if you had water that is at this temperature, and then you had like ultra cold water being forced into this thing, until you realistically start having that water at the same temperature, then it starts creating like little like forces upon it, right? So you'd have bubbles, different densities acting out within it, expanding out. However, when those different densities expand into the already formed pool, it displaces the rest of the water at first. Okay? It displaces it. So the reason why the universe is expanding is because the dark matter is displacing our current universe. There are little pockets where time is not at the same density as ours. They will, because their time is going way, way faster in there. At some point, this all catches up, as in the water at some point will, given enough time, be at the same temperature.
As physicists say, the pull that comes from the expansion is just too weak. The same goes for solar systems and planets. And atoms are held together by much stronger forces, so atoms in intergalactic space also don't expand. It's only the space between them that expands. How do we know that?
Because it's being displaced.
The universe
Wake
expands
up.
and it's not that we shrink?
Well, to some extent, that's a matter of convention.
Remember that Einstein says you are free to choose whatever coordinate system you like. So you can use a coordinate system that...
Okay, explain to me. If you see a bunch of galaxies being pushed away out in the universe, do you then start seeing what you call dark matter at the center of that? Everywhere, if you see all these dimensions just being forced apart, at the center of it is there dark matter. Because wake the hell up.
has yardsticks which expand at exactly the
My
same
argument
rate.
is there is dark matter here. It's at a different density, space-time, meaning its space isn't going at the same speed as ours. It's newer. Thus, it's faster. It's at a faster rate. So it pulls out into our universe, becomes this giant basic pool of a different density. When that density eventually meets our time, it hits equilibrium. You probably get like a flash of light, and then you discover, holy crap, look at all the galaxies already there. Because however many billions of years our universe has experienced will eventually happen in these dark things. Because time is relative. Time is a density. So, if there's a universe that we're expanding into, it's kind of older, but at some point we will be at the exact same time. Meanwhile, it was still an older universe. That's the quandary that's really, really hard to wrap your brain around. That both there's new patches of universe that if you went back billions of years would have looked like dark matter. However, when you go into it, it's as if it's been here all along. That's the part that really blows your mind.
It does the universe. If you use those, you'd conclude the universe doesn't expand in those coordinates. You can indeed do that. However, those coordinates have no good physical interpretation. That's because they will mix space with time. So in those...
So time doesn't seem to make sense, right? That's what we're saying? Like time might be different in those coordinates.
Those coordinates,
possibly.
You can't stand still. Whenever you move forward in time, you also move sideward in space. That's weird, and it's why we don't use those coordinates. The statement that the universe expands is really a statement about certain types of observations.
Okay.
That's one of them.
Well, anyways, you can end up watching the rest of her video. Take care. God bless.